Program.
Hello, my name is Ramy. I'm a PhD student at Northumbria University, Newcastle, UK. So the title of my presentation today is a multidimensional digital twin use cases classification framework. So before I take you through this framework, let us just start with a quick introduction about digital twins. So what is a digital twin and what is the concept of a digital twin? The concept of digital twin is, or the definition in simple words, it is a virtual representation of reality. So basically, data are collected from various sources and analyzed to gain insights and create value. The concept itself, or the idea of a digital twin, has been gaining increasing attention in the realms of urban planning and city infrastructure management and the built environment as a whole. So for example, one of the most popular, if not the most of all, and probably the most ambitious as well, digital twin project within the built environment is the National Digital Twin in the UK, which is undertaken by the Centre for Digital Build Britain. And this shows clearly how this whole idea of a digital twin has been gaining grounds in the urban planning, urban environment, and the built environment as well quite recently. So in support of this movement, advocates of digital twins are interested in identifying and grouping the different digital twin use cases. So basically, they are trying to demonstrate the value and the potential of digital twins and get the buy-in from everyone else by doing so. The only issue now is that, however, such endeavors have been largely ad hoc with no clear framework to help categorize, classify, or differentiate between the different groups or the different users or the different digital twin use cases themselves. So for example, and I brought a few examples here. On the very top in figure A, you can see that digital twins can be generally and broadly categorized based on the purpose or the ultimate goal of the application. So we have digital twins for either improving places or retrofitting existing assets or managing resources. In figure B down there on the left side, this circle shows another framework that has been seen by the authors of this framework as corresponding to the four key areas of applications. These four distinct areas within the circle corresponds to the four major areas of application. We have another framework here in figure C, which is showing three overlapping circles representing the three pillars of sustainability, social, economic, and environmental. And based on this kind of sustainability-driven framework, you can then start mapping the different digital twin use cases to identify to which dimension of sustainability a digital twin use case corresponds to or is relevant to. And finally, down there, there's another example as well. It includes three overlapping circles, but this time they correspond to, again, to areas of application, whether it's strategy and planning, managing assets, or assurance. So the question now is that we are trying to address is on what basis shall we classify or distinguish between the different digital twin use cases? We need a clear framework that can capture all of these different and various dimensions. So we started with following a framework development methodology, including three major steps. The first one is data extraction. And this basically included a systematic literature review by reviewing literature and searching first for studies using a combination of keywords like the ones listed down there: city, urban, infrastructure, digital twin, smart city, big data, data-driven planning. And then after conducting this systematic literature review, we have retrieved final final number of 89 potential studies. And through the step of synthesis, we try to qualitatively analyze the content of these 89 studies in order to identify the key characteristics of the digital twins used within these studies. And then at the last step, which is development, we try to use these identified features of digital twins to create fundamental standard dimensions that would help us constitute the framework we're talking about, which is the digital twin use case classification framework. So the identified features, as written down there, are grouped and aggregated into fundamental standard dimensions. It's important to mention here that the second and third steps, the synthesis and development, were carried out or undertaken in an evolving iterative manner. So when we start now talking about the framework that we have developed, at the core of this framework, we have the digital twin general use case purpose. So any digital twin must have a purpose, and it is ideally and typically articulated in the form of a verb followed by a noun. So for example, a digital twin that is developed to optimize traffic. So optimize traffic is a verb followed by a noun that explicitly and clearly articulates the general purpose of the digital twin. We start then building the different dimensions of the framework. The first one is the application area. So any digital twin use case must take place within an area of application. And digital twins have proven so far to be able to cut through various areas of application. We have listed 9 there, so including futures planning, asset management, risk and resilience, crisis management, user and demand management, environmental and carbon management, waste management, resource management, and asset registration. So these are different areas of application, and a digital twin use cases or a digital twin use case must lie or target some area of application. And then another attribute of any digital twin use case is what we call federation. So this determines whether the digital twin is capturing a subsystem, like for example, a train. So this is an individual or even a group of trains, a group of identical infrastructure assets. So this is the subsystem level of federation, or at a higher level, the systems level. And this includes a network of different connected assets, like but still within the same domain, like all means of transportation, including trains, roads, ferries, etc. And then at the highest level is the system of systems level of federation, and this includes studying the complex and interdependent integrated networks from different domains, like for example, analyzing the interdependencies between the whole network of transportation and the electricity network as well. So this is for the federation, and then comes the layering, and this is also another important feature of many digital twin use cases, where a digital twin may diffuse across different city layers. So we've been mainly talking now about infrastructure, but infrastructure assets are just a one layer within the urban environment. We do have 3 more layers, including the built environment, and this includes all types and kinds of buildings. We also have the socio-economic environment and the natural environment as well. And one digital twin use case may cut through all 4 layers or just one layer. It depends on the use case and the purpose of the use case. We then, in terms of the output of a digital twin, the output may vary in terms of the spatial scale and the spatial resolution. So we have identified 4 different levels or scales or levels of resolution, which are the, on top of all is the national, and then the city, the neighborhood, and finally the individual. And it is very important here to distinguish between the scale and the resolution. So, for example, one of the digital twin proof of concept studies created a digital twin that spatially covered the whole of the UK, but it was able to support the visualization of some sort of an indicator. It's called livability for every neighborhood within the UK. So now you do have a digital twin that has a national scale, but it goes to the neighborhood level of resolution. So this is in terms of the spatial output or the spatial scale and resolution of the output. Now there's also the temporal side of the output. So we have the temporality and the temporal resolution of the digital twin output. So this gives us three possible types of digital twins. We start with the static digital twin, and this is a digital twin that generates a static output based on an input that includes no temporal information, like for example, the underground asset register. The second type is the dynamic offline digital twin, and this is a digital twin that is fed by a chunk of previously collected and stored spatiotemporal data. So we do have now some temporal data, but it's not live. It's previously collected and stored. So this still provides us with a dynamic or a dynamic output or some sort of a simulation, but it is still, it represents spatiotemporal data that have been already collected in the past. And then we do have the dynamic online digital twin, and this is a digital twin that is tied up in an enduring connection with the twinned real entity or asset, and it constantly receives up-to-date influx of data. Thus, it can never go obsolete as long as this live digital thread persists. And this is all representing the temporality of the output. There's also the resolution. So the second and third types, which are the dynamic digital twins, either the offline or the online, must demonstrate a level of temporal resolution. And this, the resolution indicates the temporal steps or the increments by which the digital twin output changes. So whether the temporal data is being updated every minute or every hour or in real time, and so on. So the one more very important dimension within this framework is the life cycle stage, and this indicates whether the digital twin is targeting a specific life cycle, a specific stage within the life cycle of the asset, starting from the initiation, design, construction and assessment, operation, to the redevelopment and rehabilitation, and finally decommissioning. And perhaps a digital twin may also service different stages, or just one. It depends on the purpose. And finally, there's also the digital twin actors and asset stakeholders. And this dimension is more concerned with stating the people or the parties who are concerned or interested in the digital twin we are currently studying. So there are the asset stakeholders, and these are the group of people who are more relevant to the asset, the real physical asset that we are talking about. And this includes the developer, the infrastructure owner, the operator, the service provider, the consultant, and so on. And there are also some people who are interested in the digital twin project because they are concerned with the digital twin artifact itself. And these include the digital twin owner or the data author, the data host, like the cloud services and so on, the digital twin developer, and this includes the technical experts who are capable of developing the digital twin, and the data scientists who are responsible for cleaning and analyzing the data and producing the insights we're looking for. So by this dimension, we conclude and we complete the framework. As we can see, it includes the core, which is the purpose, in the middle of it, and 7 dimensions all around. So finally, to conclude, again, we have to confirm, so what is the benefit of this? There are 2 major contributions of this framework. One is before conducting digital twin projects and one is after that. The framework, when talking about before the project, the framework enables digital twin developers and practitioners to clarify and refine their proposed use cases at the outset of a digital twin project, ensuring that each dimension is fully considered, which can then support and facilitate proper and accurate digital twin procurement processes. So you will make sure that no aspect is ignored, no attribute is overlooked, but you will go from one dimension to another and accurately specify how your digital twin will look like. And then after completing the digital twin project, you can then, the framework can then enable the digital twin researchers to identify the trends amongst all the different kinds of digital twin projects, and identify also the gaps across the digital twin world by examining which dimensions or levels or scales have been more addressed than others and which ones have been more ignored. And then we can better understand what's going on with the digital twin projects and direct our future research. So that's it for me today, and thank you, and I'm happy to receive any of your questions.